So back to yesterday, we had talked about the limit comparison test. Oops. And the version of the limit comparison test I gave is we have two series, some of the A sub n's and some of the B sub n's. And one of these has to be known. So let's assume that B is my known series. And so A is the one that's unknown. And the theorem I went over is that if the limit as n increases of the ratio of their terms, if that goes to some positive finite number, then the series both converge together or diverge together, okay? So we talked about edge cases the other day with respect to p-series and tweaks of p-series, but here we have some edges to explore too. So I said positive. Well, 0 ain't positive. What if you get 0? Usually getting 0 is not a bad thing. So those are the edge cases. So let's break those out. Come on, color, there we go. So one possibility is, well, what if the limit instead goes to 0? You'd think, oh, that should be good. A sub n over B sub n. This can only be used to show convergence. So the sum of the A sub n's converge if the sum of the B sub n's converges also. But if B sub n, my known series, happen to diverge, then the 0 doesn't actually tell me anything. So that's dangerous. Going the other way, the other edge, the opposite of 0, is infinity. And so if the limit as n increases of our A sub n over B sub n, the ratio of our terms of the two different series, if that happens to grow without bound, then, come here, pen. There you go. Then the A sub n's diverge if the B sub n's also diverge. And I'm still assuming that B sub n is my known series, A sub n is my unknown series, something new. Okay, so that's the edge of that theorem. It gets a little fuzzy there, so you got to be careful on the edge. So usually if I hit one of those edge cases, I usually see if I can find another way to test the series just to make sure I didn't get the edge case backwards, because it's easy to mess these up. So let's look at an example of this. So again, a 0 is, so pretty much we want the ratio of the terms to be some positive number, 1, 2, a half, pi, whatever. Everything works out nice that way. If it happens to be 0, I can only show convergence. If it happens to be infinity, I can only show divergence. Okay, so 0 convergence, that kind of makes sense. Infinity, hey, that's divergence anyway, so kind of makes sense there too. But every once in a while, I kind of mess that up, so I'm always looking for more than one way to check. So let's take, for example, the sum as n goes from, this should work, 1 to infinity, of the natural log of n over n squared. So we know 1 over n squared, the p-series, is convergent, but now I'm multiplying some number into the top. Okay. Now, if I had just multiplied an n into the top, right, n is bigger than the natural log of n at any stage, that would be 1 over n. So just curiosity, kind of thinking about, what the heck is this like that I know? I might say that if I look at n equals 1 to infinity of n over n squared, well, that's the same thing as the sum of the 1 over n's. Then this thing might diverge. On the other hand, I know the natural log grows way slower than the straight line n, So maybe I have a hope for convergence. So I just have to throw a shot out in the dark and see what happens. So I'm going to try this right here and see if it goes anywhere. Now, a direct comparison isn't going to be useful here because n is bigger than the natural log, so I have my inequality going in the wrong direction to show divergence. I have a divergent series above the unknown series. No help there. Okay, so I'm going to try the limit comparison. So then I take the limit as n increases, and let's write it as this unknown guy in the top. So natural log of n over n squared divided by 1 over n. Multiplying by the reciprocal of the denominator gives me natural log of n over n squared times n over 1, and we get a wee bit of cancellation there. Limits as n, infinity, n goes to infinity of the natural log of n over n. Now, just thinking about the graphs of those guys, my numerator, is that line right there, and my denominator, oh no, backwards, sorry, that's my denominator. My numerator is this guy over here, which grows but wicked slow. Okay, so just by thinking about the graphs, given that this is the natural log of n, and this is y equals n, probably should have wrote that in blue, color code. What do you think is going to happen with this limit? What's that? Do you think it's going to diverge? Which is growing faster according to my graphs, the numerator or the denominator? The denominator is growing fast. So I think if the denominator significantly outgrows the numerator, then the denominator is going to be way bigger. If you have a fraction with a way bigger denominator, you should be heading towards 0. So I'm guessing this might go to 0. Now, I just have an intuition on that based on the graphs. That's not concrete proof. So this is really an indeterminate form, infinity over infinity, and I can apply L'Hopital's rule. So I'm going to do that. So applying L'Hopital's rule, this now becomes the limit as n grows. Derivative of the natural log, 1 over. And the derivative of n with respect to n is just 1. Oh, nice. So I get 0 in the top, 1 in the bottom. This does go to 0. N does way outgrow natural log of n over time. All right. So let's see, where does that leave me? Nowhere. Okay. What do I do next? That leaves me nowhere, right? Because the 0 can only be used to show convergence. Unfortunately, this guy up here diverges. How about we try comparing it to 1 over n squared? See what happens there. Maybe this growth in the numerator is so insignificant, it's a lot like 1 over n squared instead. All right. Now, as far as a direct comparison goes, if I say what's happening with 1 over n squared versus what's happening with the natural log of n over n squared, since I'm multiplying something into the numerator, each of these terms is bigger than that one. So I have a convergent series below an unknown series, which is a direct comparison would be useful there. So that's why we have the limited comparison. All right, so let's try it. Limit n goes to infinity of the natural log of n over n squared, all divided by 1 over n squared. Flipping that denominator, we get the limit. I don't know, I already wrote the limit, sorry. I was meant to write ln. There we go. We get the ln of n over n squared times n squared over 1, which is the natural log. And I know that the natural log over time grows forever, so this diverges, increases without bound. What does that tell us? Nothing. Yeah, sometimes you'd keep trying stuff and it's like, oh man, we don't have the right tool yet. Not sure what that thing does. All right, so let's see. One thing we skipped was the divergence test, but the divergence test, if you just ignore the sum and just look at these guys right here, n squared way outgrows natural log of n, it's going to go to 0, which means still don't know anything, right? Which is, sorry, I skipped that part, which is why we came here. So sometimes what I'll do is I'll list the terms to see, maybe I can look at it and decide just numerically, oh man, this is not a good thing. I should stop looking at it. So I'm just going to go over here and plug it in. So we have the natural log of, what am I using here? I. And down here, I have I squared, right? Right? And I only have a few terms there. Let's extend it out. I think I need to fix this graphing thing. Let's go out to 50 maybe. And y can go from 0 to 2. All right, so it doesn't look like it's settling down enough at 20 terms, so I probably should go out farther. Let's see, how do I do that here? I just come up here and, no, let's see, I gotta click there, don't I? Yeah, there we go. Oh, wrong button. Let's go out to 100 maybe. And is it settling down? Gotta look more out to the right. Let's see, can I just grab this thing and drag it? Oh yeah, look at that. Yeah, I don't know. It's unclear to me whether it's settling down. It looks like maybe a square root type function possibly, or possibly a logarithm. Both the square root and the logarithm grow slowly, but forever. So I'm at a point where I've exhausted all of the tools I have at the moment, and I don't know what this series does. Okay, we need more tools. So the tool I'm about to present actually isn't going to help with this series, but maybe the tool I present on Monday might, or the one I present on Tuesday. We got a couple more tools before we move out the power tools. And Jesus was looking online for a summary of possible series tools, and he found a list of pretty much everything we're covering. The last one was one called Taylor series. And although we spend about a day or so on all these other tools, Taylor series we're going to spend about 2 weeks on. It is the biggest, most powerful tool we will learn this quarter. All right, so next topic. So this one is a big unknown. We're going to come back to you later. We need more tools. I'm not saying. Question was, is it divergent? I said, I'm not saying. So it's a strange edge case, which we will analyze some more another day. That's the other thing you got to get used to in math, and I think you guys wouldn't have gone this far. You got to get used to delayed gratification in math class. Sometimes you just got to wait a while before things finally work out. So we're going to look at what are called alternating series. And alternating series come in a couple of different classes. One, which we'll spend most of our time, is the idea of series that are strictly alternating. So a strictly alternating means every other term has to change sign. Okay, so an example would be 1 minus a half plus a quarter minus 1/8 plus 1/16 minus 1/32. If I wrote that in summation notation, I might say this is the sum as I goes from, I think I'll start with 0 here, to infinity, because I have the dots on the edge there, of -1 over 2 all to the power I. Right, so if I is 0, I get -1/2 in parentheses to the power 0. Any non-zero term to the power 0 is 1. Okay, when I is 1, oops, I get a plus -1/2 to the 1, and then a plus -1/2 squared. And so the powers are killing the sign because they're even powers every other term. Okay. Sometimes what we'll do is we'll rewrite a series like that to pull the negatives separately out, not out of the sum, but just just separate the positive and negative parts. So I'll write this as -1 to the I times 1/2 to the I. So if the series is strictly alternating, we should always be able to separate the alternating part from the positive part. And then what we do from there is we analyze the non-negative part right here. So if I then focus on this non-negative part, I can then tell you some things about what's going to happen. So this is the non-negative portion. And let's see where I didn't print that one out. So often we'll write an alternating series like this in general. I'll use an n this time, from 0 to infinity of -1 to the n times some bn. And the condition is these bn's are positive, or at least non-negative, excuse me. Which means they could be 0 or positive. And then there's other kinds of series that alternate, but not so regularly. So you could end up with a series that looks like 1 minus 1/3 plus 1/5 plus 1/7 minus 1/9 plus, what would be next, 1/11 plus 1/13. And maybe there is a pattern to the alternating, maybe there's not. Okay, and that can be engineered to happen in a few different ways. So this guy right here is not strictly alternating. Okay. And that causes some complications. When it's not strictly alternating, it's much harder to analyze it. Because with the alternating thing, if it does change every other term, then it's much more predictable in how we can zero in on what's happening with it. So let's take a look at a couple of these and see what happens. Let's see, which one do I want to start with? That one we just did a minute ago is a good one. So let's take back that sum as I. It's an I, goes from 0 to infinity of -1 to the I times 1/2 to the I. So this is what we call a strictly alternating series. Oops, that's supposed to be an I there. No. If I just look at this positive version and I think about the divergence test for a minute, the divergence test says, what's the limit of the terms as n gets big? Well, 1/2 to the n, that's going to go to 0. We looked at that before. So the divergence test at first glance doesn't tell us anything, but when I combine it with something that's strictly alternating, then what I get is convergence. Okay, so just a note, there's a thing called the alternating series test. So 1, if it does strictly alternate, and 2, if the limit as n increases of those bn's, those positive terms, if those guys go to 0, then we have convergence. Okay, so we got to have it strictly alternating. So that means we're looking at things where we can pull out a -1 to something. Now, it doesn't matter whether the first term is positive or negative, that's irrelevant. As long as every other term changes sign, we're good. And then as long as the individual positive pieces, as long as they're going to 0, it's going to converge, which is kind of nice. So back to this black one up here. So according to the alternating series test, that series right there should converge to something. Now, if I write it back in the way I did the first time, when I said it was n goes from 0 to infinity of -1/2 to the n, this is a geometric series. Geometric series is when you have a fixed base to a power. And the geometric series theorem basically says if the absolute value of your r, your ratio, your base, if that's less than 1, then you have convergence. Now, the geometric series theorem tells me more than the alternating series. They both tell me I have convergence, but the geometric series tells me what it converges to. So remember, a geometric series, if we consider it to be the sum as n goes from 0 to infinity of some fixed number times some base to a power, I should write that as an r, excuse me, r to the n, then this will converge to that fixed multiple, which is also the first term, if we start with 0 over 1 minus r. So for my series here, I can consider I have a 1 multiplied by the front there. So my numerator, this thing should converge to 1 over 1 minus -1/2. So that would be 1 plus 1/2, which is what, 3/2, flip 3/2, and you get 2/3. So this should converge to 2/3. So let's check it out with a computational tool to see if that really happens. All right, where's my computational tool? Right here. So what do I want? I want the whole thing. Okay, parentheses, -1 over 2 raised to the power I. Oop, wrong place. Raised to the power, there you go, I. All right, and I want to start this at, how do I get to the denominator at the bottom? Come here, there you go, 0. Ah, there it is. Where is it heading? It says I'm heading to 0.6667-ish. Looks like 2/3 to me. Yeah, and it heads there, relatively rapidly. This isn't showing us a lot of decimal places, so I could just double check by saying, give me the sum as n goes from 0. Oops, I can't use n here. Let's use k of -1 over 2 raised to the k. Ooh, I need to give it a star ending point. Let's go out 100 terms. And it's giving me a lot of 0.6s there at the bottom. What if I only went out 10? If I go out 10 terms, I have what, 1, 2, 3, 2 or 3 places of accuracy. If I go out 20 terms, 1, 2, 3, 4, 5 places of accuracy. If I go 20 terms out, not bad. It's converging pretty quickly. All right, let's try another one. What about the sum as k goes from 1 to infinity of -1 to the power k plus 1 over k. So I should list some terms out. It's always a good idea. If k is 1, I get -1 squared over 1, which is 1. If k is 2, I get -1 cubed, which is a negative. So that would be 1/2. If k is 3, I get an even power on the -1, so it's going to be positive. So that's going to be 1/3. So I have 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, and so on. This is the alternating harmonic series. All right, so let's see. Harmonic series on its own diverges. We've tested that out in a couple of different ways. We had 2 different tricks to prove that. But here, I'm occasionally subtracting something, right? Start with 1, take away 1/2. All right, let's add 1/3, then take away 1/4. Am I taking away enough stuff over time that this is going to converge? Well, let's see. Is it strictly alternating? Okay, so we do have strict alternating. If we ignore the negative stuff and we take the limit as k goes to infinity of the rest of my term, which is just 1 over k, right? What does that do? Goes to 0, right? According to the alternating series theorem, this has to converge. This does converge. Ooh. But to what? Let's play. All right. So it does converge according to the theory. I'm going to ask where it goes. So let's see. We don't have a power. Oh, no, we do need a power. Let's put you back in there. Am I still in the exponent position? Looks like it. I plus 1. Let's make that just -1. Ooh, where'd that come from? Times, no, divided by, excuse me, I. Oh, and I want to start off with 1. I get that right? Yeah. Okay, so I just need to adjust the window a wee bit. Oh, my power is wrong. Oh, I'm doing, yeah, so yeah, I'm getting the, if I mess up the positive -1, I get the opposite of the answer I wanted. Does that make sense? Because that just switches where the negatives go. So that should be a plus. Oh, that's where the +1 went. I see now. What? No, no, go back up here. Okay, maybe it needs parentheses. All right, I plus 1. What? +1? There we go. Ooh, look at that thing wiggle. That's cool. All right, so let's see. Let's back off here a minute and then change the scale. Okay, so here we can see at first we get some radical bouncing around, but then it's starting to settle down around some number. Ooh, what number are you? Let's go out here to where they look way closer together. That one says they are settling down to about 0.68-ish. 0.68-ish. Huh. Wonder what 0.68-ish could be. That one says, what's this one? 0.69. So somewhere between 0.69 and 0.68 is a special magic number. Square root of 2 over 2? Square root of 3 over 2. Square root of 3 over 2, maybe? No, never mind. It's close. It's close to that? Square root of 3 over 2? Oh, interesting. SQRT of 3 over 2 is 0.86-ish. This looks like it might be a little heavier than that, a little higher. Could it be some relative of pi? Let's see, pi over 3 would be 1. So pi over 4 maybe? 0.78, it's not pi over 4. Huh, wonder what this guy is. Interesting. Where could we go to ask? Who knows a lot about math? Maybe I just need more terms. All right. Let's back up ahead. Oop, where'd I go? Oh no, I want you up here. There you are. All right. Maybe I need 200 terms. Let's oops, take this out farther. 200. Enter 200 and then whip way out there. Better change the scale. It's getting hard to see. Let's say I want you. And zooming in on something there. 0.69-ish. The one before it was still about 0.69-ish. Yeah, okay, so somewhere between 0.69 and 0.695. It's the natural log of 2. Oh man, that is right on track. The natural log of 2. That seems too close to ignore. All right, so we have a hypothesis. Did some website tell you it is, or your calculator? Oh, your calculator just, you put in infinity and it said, hey, that's a natural log of 2. Oh, this sucker has a computer algebra system. Wow, score. Yeah, okay, so since, yeah, so let's go to Wolfram Alpha, which is an online computer algebra system, and say, hey, we're curious about the sum of -1 raised to the power n minus 1 divided by n. Yeah, I think that's it. And Wolfram Alpha thinks for a moment, and it says the natural log of 2. Yeah. And it gives us a lot of decimal places. This is kind of cool. I don't know if I showed you guys this before. There's a more digits button, which I can just keep hitting and hitting and hitting and hitting. Eventually, it'll tell me to knock it off. But the natural log of 2 is like pi, like e, is an irrational number. It never repeats a fixed pattern over and over again. It's always, it's not, you can't say it's random, but it kind of is. It's this really weird stuff going on with irrational numbers. Natural log of 2 is even better than irrational. It's called transcendental. And the difference between transcendental and other kinds of irrationals is the square root of 2 is the solution to the equation x squared equals 2. Okay, so if a number is a solution to a polynomial equation, and the polynomial equation had coefficients that were normal kinds of numbers like fractions, it's just a regular irrational number. If the number is never a solution to a polynomial equation, it's called transcendental. So pi, e, natural log of 2, those are all numbers that aren't ever solutions to polynomials. So they're a special kind of irrational number, for whatever that's worth. Transcendental, it makes them sound, I don't know, like they're mystical somehow. It's better than imaginary. Imaginary, they got such a bad name because they aren't imaginary at all. I mean, the lights rely on imaginary numbers. Our computers, our phones, our toilets flush right, all because of imaginary numbers. They're so real. Okay. But they're not real. Man, I want to just go back in time and grab whoever coined that phrase and say, no, you can't do this to us. You're causing mass confusion in the future. All right, let's do another one of these. That was fun. Oh, actually, no. Let's do something else. We're not going to do another one yet. Turns out alternating series can actually tell us where the how far off we are from the real answer. So I'm going to try to draw a picture of that. So let's think about the way we were graphing that series, where I had the y value was the actual partial sum, and the x-axis, that's just my n. Right? And so we had a series that was jumping around. Like the first term was way up here, and then we got to subtract away from that. So the second term ended up down here. The third term ended up over here. Fourth term put us down here. So we got this kind of zigzag pattern going with the sequence. So I'm going to connect those dots just for fun. Let's see, how do I do that? Okay, so we had our first term, and then we got to take away something, so our sum dropped down. So I'm not graphing the terms, I'm graphing the partial sums here, right? Then I got to add something, like, so first we had 1, we took away a half. Then we gained a third, but then we took away a fourth. then we gained a fifth, then we took away a sixth, then we gained a seventh, then we're going to take away an eighth. Okay, so what's going on here? There's some really interesting stuff happening if you dig into this part. So remember, S sub n is coming from this sum as I goes from 1 up to n of some alternating negative term. I'm going to call that negative 1 to the n plus 1. Now, sometimes you'll see that as an n plus 1, sometimes as an n minus 1. It doesn't matter whether it's n plus 1 or n minus 1. It's still going to cancel things in the right. It's still going to make things positive or negative in the right order. But if you switch n with n plus 1 with n, then you get your signs in the wrong spot, which is an easy thing to do, right? I mistyped it earlier. So that's one thing you always want to be conscious of. Is your first term supposed to be positive or negative? That's going to depend on your starting point and whether you choose this to be n or n plus 1. All right, and so then we have our terms, the bn's. And remember, our bn's have to be the positive things, okay? So if I kind of zoom in on the axis here to figure out what's going on here, this right here is my first partial sum. This guy down here is my second partial sum. To get from my first partial sum to my second partial sum, I have to subtract the second term. And then over here, that puts me at my third partial sum. And in order to get from the second term, the second partial sum to the third partial sum, I had to add B3. Then I'm going to get over here to the fourth partial sum that lives around here, S sub 4. How did I get there? Well, I had to take away what? B sub 4. And then I'm going to add a B5 and so on. So I have my partial sums, and I also have my jumps to get there. So these tell me how to jump to get from one sum to the other. And the sign tells me which direction to jump. But notice I'm always going up, then down, and up, then down, and up, then down, okay, because I have that strict alternation. So the cool thing here is that if I look at, for example, S sub 5 is going to be right here. The difference between the two partial sums, like S5 minus S4, and let's just do that in absolute value, that's going to be that term I had to add on to get there. So B5 is going to be that one. Now, ultimately, what I really, really, really want is there's some limiting value that I'm converging to here, L. Now, since it's a sum, instead of an L, we usually call it an S. All right, so I guess I should get rid of that. So S is the limit of my partial sums. And these things are complicated. It takes a while to get used to them because we got multiple things going on here. We have the individual pieces we have to add up. And then since we're human beings, we can't add every single number in existence. We have to do partial sums. But then we have to take the limit of those partial sums to see if it actually goes somewhere that I can count to. Okay, so there's like 3 things all wrapped up in this puzzle. So S is somewhere in the middle here. Okay. So I can take this inequality a step farther. If I want to know how far S sub 5 is away from the actual S, notice to get from S4 to S5, I had to jump past S to get there. Okay. So what that means is, since you had to jump past the limiting value, that next term here has to be bigger than the distance from whatever term you want to the actual sum. Which is kind of neat. Now, I can take it a step farther. let's see, I'm kind of running out of colors here. S6 is going to be somewhere down here. And so the next term after S5, the difference between the fifth partial sum and the actual sum is actually less than that next term also, right? And think about it, what's bigger, B5 or B6? No, which is bigger? Yeah, B5 is bigger. These things have to, the B's have to be going, they have to be shrinking consistently. If they don't shrink consistently, this doesn't work, okay? So so basically what I've calculated right here, isn't that error number 5? Remember we talked about partial errors before? And I can actually replace that 5 with a 6, and I can get away with it because of what's going on in there. So we get this general theorem with alternating series. This is only for alternating series. Alternating series remainders. Okay, remainder is really another term for error. How far off we are. So my error, oops, not a sum. My error for any amount of terms in absolute, now here I have to use absolute value because I'm alternating signs, is always going to be equal to the difference between the actual sum and whatever partial sum you're at. That's my infinite tail after wherever I stopped. Right? We have our partial sum, which is finite. That's good for human beings. We do finite things. We have this infinite thing that's blowing our minds. What is that infinitely long tail doing? And it turns out we can always say that's going to be less than or equal to the next term in line. The next thing I was about to add or subtract. Now remember, the B's are always positives. We separated out the plus or minus thing, right? The minus part. Okay, so that's kind of cool. So if I'm playing around with that natural log of 2, so if I look at like partial sum 100 would be the sum as I goes from 1 to 100 of -1 to the n plus 1 over n. That's that 1 minus a half plus a third minus a fourth, that alternating harmonic series. Now here, I'm only going up to 100, so I'm going to write plus ... and then let's add 100, it's going to be a negative. And this is the end of that series. I'm skipping a lot of terms, right? I'm skipping term number 101 and 102 forever and ever and ever. And what the theorem says is that the error, that infinitely long tail from number 100 on, has to be less than or equal to the next term. Well, what's the next term? 1 over 101. So I am less than that far away from the actual sum. So let's see, what does our partial sum calculator tell us here? Let's see, that's the wrong series. -1 to the k, no, got to do parentheses, to the k plus 1 divided by k. And where did I say I was going to go out to? 100? Oh, I started at 0, sorry. Starting at 1. Yeah, so we got to pay attention. What are we starting at? What are the powers? Are they alternating in the right order? So this says 0.688-ish. 1 over 100 is 0.01. So 1 over 101 is going to be a little bit less than that, which means this should be accurate to 2 decimal places if I round. So this says it's about 0.69. So this sum right here is approximately 0.69. Now we happen to know the answer. We happen to know the answer is the natural log. So let's just double, I know time's up, but let me just continue this real quick. If I find, well, what is 1 over 101? It's 0.00990099. It's got a lovely rhythm to it. And if I go back to my partial sum calculator and I say, okay, let's take that partial sum and subtract the natural log of 2 from it, I should find that number right there in absolute value is smaller than 1 over 101. 1 over 101 was 0.009. This is 0.005-ish. So yeah, it works. Okay. So even if I can't say, now we don't have a reason this is true yet, except this computer system says, hey, it is the natural log of 2. We still need to prove that for ourselves. And we will do that in a couple of weeks once we get that Taylor power tool in our belt. But we can at least say we know how accurate we are up to a certain point now. Okay. All right. So have fun with that tonight. Let's see. We don't have a regular meeting tomorrow, but if anybody wants to get together, I will be around. And the next thing is to do what's called absolute convergence, which isn't the way we use the word absolute in regular life. Like if somebody says absolute to me, I mean, it means it's got to happen. Here, absolute means absolute value, right? So it should be absolute value convergence, not absolute convergence, but we'll talk about that on Monday.